A beam is a structural element that can primarily withstand loads that are applied along its axis. When a load is placed on a beam, it generates response forces at the beam supports point, causing a curved deflection mode. The combination of all the forces acting on the beam result in internal stress, strain, and deflection, as well as shear force and bending moment within the beam. Beams can be classified based on their length, material, cross-sectional, and shape. There are several types of beam, which is cantilever beam, simply supported beam, overhanging beam, continuous beam, fixed end beam, and a combination of cantilever and a simply supported beam. Deflections, or the term that means the displacement of a structural element under load, can be determined by integrating a function describing the slope under load. Common method for calculating deflection is one of it is Macaulay method, which describes the distributed loading and allows for a single equation for the bending moment along the beam, also known as the discontinuity function. Or the other method is direct integration, which uses the radius of curvature and internal moment in the beam to calculate deflection. As for the objectives, our group has three main objectives in this project. The first one is to calculate the deflection of beam. The second one is to show the bending moment on a beam caused by a load. And lastly, to relate the relationship between load applied and the deflection of different type of beam.
So now I will present about the experiment apparatus and the experiment procedure. For the experiment apparatus, we have mainly used the three kind of the bar. They have aluminum bar, steel bar, brass bar. The bar is paired as the test specimen, and the second apparatus is the rod. For each, the rod have 10 Newton, and the third is the vernier caliper. The vernier caliper is used for measure the width and the thickness of the bar, and the ruler is measure the length of the bar. And the beam apparatus is to hold the bar to process the whole experiment. And the last is the deflection gauge. The gauge is to measure the deflection of the test specimen. So next is the experiment procedure. For the first step, we need to measure the length, thickness, and the width of the bar with the ruler and the vernier caliper. The second step is take the bar and fix the deflection gauge at one point. We set out the value as the zero. The third step is pull out the rod in the hanger and put at the point L, which is the 0.7 meter from the starter point. And the fourth is record all the value on the deflection gauge. And the last step is change the different material bar and repeat the step from 1 to 4.
Right? Now we move on to the calculation part. So as you can see here, it is the material specification. So we have here the length of the bar, the base, and the depth. In our group, we studied three types of bars, which are brass bar, steel bar, and aluminium bars. Alright, we move on to this part. So as you can see here, we have three different values for the young modulus for our bar. As you can see here, we have brass bar, steel bar, and aluminium bar, which all of the three materials give us different value of young modulus. In our project, we fix the length of the bar, also the base and the depth of the bar. So by using this information, we can calculate the moment of inertia by using this formula, which is BD cubed over 12. The moment inertia is used to find further calculation for the deflections of the bar.
This is the table of the experimental deflection and theoretical deflection. The, exper- the theoretical deflection using the formula y equals to p over 6 ei times with negative x cubed plus 3l square x minus 2l cubed, and the percentage difference using theoretical minus experimental value over theoretical value times 100%.
Alright, we move on to the last part for the calculation. So here is the graph for the deflection for experimental and the theoretical for the different materials at fixed load, which is 10 Newton. So here are the differences.
I get to explain about the discussion. In this section, we get to discuss about the analysis of deflection in brass, steel, and aluminium under identical load. Comparison between theoretical and experimental deflection values will be also explained in this section. First, we will go to the theoretical deflection. Steel has the lowest deflection with the value of negative 2.2425 times 10 to the power of negative 3 meter, while brass has the highest deflection than steel with the value of negative 4.619 times 10 to the power of negative 3 meter. Aluminium, on the other hand, has the highest deflection with the value of negative 6.929 times 10 to the power of negative 3 meter. Well, this trend has a linear increase from brass to steel and also a linear decrease from steel to aluminium. Moving on to the experimental deflection. First, brass has the lowest deflection with the value of negative 2.24 times 10 to the power of negative 3 meter, while steel with a higher deflection than brass with the value of negative 2.72 times 10 to the power of negative 3 meter. Last, aluminium has the highest deflection among all of it with the value of negative 4.14 times 10 to the power of negative 3 meter. From this experimental deflection, we get to know about the trend, which is a linear decrease from brass to steel and a linear decrease from steel to aluminium. This will be detailedly explained in the previous slide. Next will be the result and the percentage difference. Well, we get to compare the result and the percentage difference from theoretical deflection with the experimental deflection. For steel, when it's compared, the percentage difference is 12.16 from the theoretical deflection compared with experimental deflection. Moving on to aluminium, it has a 40.25 percentage of difference. Last, brass has the highest percentage difference, which is 51.51%. For the final element of the discussion, we'll get to discuss on the experimental errors. For the first experimental errors would be the instrumental error due to zero error in the digital gauge. Next will be the data collection limitation. This is due to the reading taken once due to the time constraints. And finally, the impact. This is due to the inconsistency in data and percentage difference. Moving on, the conclusion. It is a culmination of learning outcomes of the cantilever beam deflection experiment. Well, first, to culminate the purpose of the experiment. It is basically to calculate the deflection of a cantilever beam and also to analyze deflection points of different materials under a constant load. Next would be the learning outcome for undergraduates. Well, this is basically to maximize their ability to learn, visualize, and identify deflection points on different materials. Besides that, the demonstration of the bending moment on a beam caused by a load. Finally, it is all about understanding the variation in Young's modulus among different materials. Moving on to the third conclusion would be the practical application. It is to visualize theoretical learning in a practical experiment. And also, calculating and comparing percentage difference in deflection of various materials. It is also about translating theoretical knowledge into real-life experiments and real-life scenarios in order to relate it with what we have learned. The fourth would be the challenges encountered during the experiment. Well, repeated use of specimens leading to earlier deflection than expected is the first challenges that we have encountered during the experiment. Besides that, potential inaccuracies due to the specimen wear. As a final conclusion, theoretical and experimental values show discrepancies. Besides that, experimental errors and limited data collection affect accuracy. Steel shows the least deflection theoretically, while brass shows the least experimentally. Last but not the least, the recommendation for improving experimental accuracies. The first recommendation would be the increase of specimen thickness. Rationally, thicker specimen will require greater force to achieve initial deflection. The impact would be it would reduce the premature deflection, leading to more accurate results. Next would be the use of specimen with higher modulus of elasticity. This suggestion is considered with the materials with a higher modulus than steel for more precise measurements. The impact would be enhanced resistance due to deformation under load. The third and the last recommendation would be the shorter specimen length. Rationally, shorter beams will not deflect as readily under the same load or with higher loads. The impact would be it will result with a more controlled and measurable deflection, improving data reliability.